Welcome to Excel 2013 Statistical Analysis video number 42. Hey, if you want to download this Excel workbook or the PDF files that go along with this video, click on the link below the video. Hey, we got to talk about the exponential probability distribution. Hey, there's a chart of it. Looks like it's real tall at the beginning, but then it gets smaller and smaller as it gets further out the x. So if we're talking about times between arrival or times to stand in line, the longer the time, the smaller the probability. Hey, exponential is useful in computing probabilities for the time it takes to complete a task or distance between similar occurrences or successes. So examples, time between arrivals at a car wash, or our example last video with Poisson, we talked about number of arrivals at a restaurant per 1 minute. We could do time between arrivals at that restaurant, and we'll look at that example. Time to take a test, or distance between potholes on a road. All right, it's related to the Poisson, but now we're talking about time between arrivals instead of number of arrivals per time period. Now, let's look at our functions. Here's our exponential density function. There it is. That calculates the height of the curve. If we use EXPON.DIST, we put a 0 to plot our curve. If we use the exponential cumulative probability formula, there it is. In EXPON.DIST, if we use a 1, it'll calculate cumulative probability from 0 to x. Now we want to scroll down and talk about the relationship between Poisson and exponential distributions. Now, down here, B, we'll start with B first. If the arrivals follow a Poisson distribution, the time between arrivals must follow an exponential distribution. Now, we'll look at our Dick's Hamburger example. That's the one we did last chapter where we had 3.88 people arriving per minute. That's the Poisson, counting people over a particular interval that are arriving. If we want to switch to exponential, that means we take the inverse of that for our exponential distribution. And for our Dick's Hamburger restaurant, that means we'd have 15 seconds between each arrival. That would be our average arrival time. Now, Poisson distribution provides an appropriate description of number of occurrences per interval, 3.88 people arriving per minute. Exponential distribution provides an appropriate description of the length of the interval between occurrences or arrival. In our Dick's example, it'll be an average of 15 seconds between each arrival. Now, let's go over to Excel, and we want to look at this very example. I'm on the sheet exponential Dick's Hamburger example. Now, if I scroll over here, here's our example from last time. Number of arrivals during 1 minute. There's our Poisson function to calculate the chart. Here's our chart. And we got busy calculating probabilities of number of people arriving in any 1 minute period. But now, in this example, we want to talk about arrivals to Dick's Hamburger at 45th Avenue in Seattle on Saturday noon lunch hour during a 1 minute period is 3.88 people arriving per 1 minute. That's what we did for Poisson. Now we're going to see the average time between arrivals is 0.2577 minutes, or about 15 seconds between arrivals. Now, because there's this relationship, if we know the mean number of people arriving per 1 minute, we'll take the inverse of that, and that'll give us the average time between arrivals. So I'm going to say equals 1 divided by this 3.88. What it means is if I take the inverse of this, it means for every 1 minute, I'm going to divide that by 3.88 arrivals. Enter. What it gives me is 0.2577 minutes per 1 arrival. Now, I actually want to convert this to seconds. This is in minutes. Now we want seconds, so equals this times 60. Now, I'd like to round this, and I want to use our rounding rule. I want to round to the actual second. So I'm looking at the 4. I need to round this to 15 seconds. F2, I don't want to do that by hand. I want to use the round function. So round will round to any number of digits. Hey, I'm going to the integer, so I put a 0. Close parentheses, and enter. That rounds to the integer, in our case, seconds. So there it is. average time between arrivals. Now we can ask the question, hey, what's the probability that time between arrivals will be 10 seconds or less? If I'm looking at this on the chart, there's 10 minutes. It's going to be all of this probability right here from 0 up to 10. Remember, the way our function will work is it'll automatically go from the lowest up to whatever x value we give it. So I'm going to do equals expon.dist. Hey, there's the x, comma, and our lambda is going to be 1 divided by our average time between arrivals. And then comma 1 gives us cumulative from 0 to whatever our x. And so boom, there's the probability. The probability that the time between arrivals will be 10 seconds or less is 0.4866. Now, what's the probability that the time between arrivals will be 30 seconds or more? Oh, here, if we look at this visually, it's above, right? So I'm going to come here. It's going to be our 1 minus. If we do expon.dist, if we put in this x, that calculates everything from 0 up to our 30, right? And so that's why we say 1 minus this. Comma, our lambda is going to be 1 divided by our average time between arrivals. Comma 1 for cumulative, close parentheses, and Control Enter. There is the probability. So 0.135 that the time between arrivals will be 30 seconds or more. Hey, I plotted this down here, and if you want to plot it, it's similar. Notice expon.dist. Now, I actually took this lambda here because I wanted this to plot, even though I didn't have these values. But that lambda right there is just 1 divided by that. Notice the 0 in the cumulative. That allows us to plot the chart. All right, now we want to go look at our next example, exponential Disney wait time. Now, for a particular Disney ride, the mean time to wait in line is 22 minutes. Distribution follows an exponential distribution pattern. So this is the average time to stand in line. And we want to calculate the probability that we'll stand in line 15 minutes or less. Now, we could use this formula, 1 minus e, and we can use exponent 1 in Excel, raised to the minus particular value divided by mu. We're going to go ahead and try that here. Equals 1 minus exponent 1. That is the method of getting e, caret, minus, and then in parentheses, simply particular x divided by our mu. Close parentheses and enter. So the probability is 0.49, almost 50% that we could stand in line 15 minutes or less. Now, if we added this to the chart down here, it would look like that. That whole area right there. Now, let's go ahead and use our expon.dist. Our particular x, comma, 1 divided by our mean. And cumulative is 1. That means we're going from the 0 all the way up to our particular x, close parentheses, and enter, whichever way you like it, the actual formula or the exponent. Now, if we want to calculate greater than or equal to 25 minutes in line, notice this formula is 1 minus. So if we did 1 minus 1, it would change. It would just be 0 there, and it would change that minus to a plus. So we can simply do the exponent equals expon 1. That just gives me my e. If I enter it, it's just 2.7182. Repeating decimals, that's that magic number. And we're going to simply raise it to minus, open parentheses, our particular x, and we're divided by our mean time, close parentheses, and enter. So the probability that we'll stand in line 25 minutes or greater is 0.32. If I add this to the chart down here, it's everything above. Now, we could just use our expon, and we'll use the same convention. We're after probability on the upper end. The expon.dist will calculate from 0 up to our x. So I'm going to do equals 1 minus expon.dist, our particular x, comma, 1 divided by our mean wait time, which is lambda, comma, 1, close parentheses, enter. And we get the same exact thing. Now we could do between. Notice we're after this. Well, we need to get rid of this and this. All the area is 1, so I can simply say equals 1 minus, and in whichever order, get rid of that one by minusing, and then get rid of the other one by minusing, and enter. We could also flat out do our rule. Anytime we're getting between, we get bigger area minus smaller area. So equals Expon.DIST. Our big X is 25, comma 1 divided by our mean, comma 1. That gives me all the area up to our 25. F2, and now I'm going to subtract Expon.DIST. The smaller x, comma 1 divided by, and go up and get our mean wait time, comma 1, close parentheses, Control Enter. And so we get exactly the same thing. All right, in this video, we talked about the exponential distribution. Great when you have mean wait times, like for a Disney ride, or you have average time between arrivals, like in our Dick's Hamburger restaurant example. All right, that's it for Chapter 6, Continuous Probability Distribution. Next chapter, we'll get to talk about the amazing central limit theorem. All right, we'll see you next video.